Well, here we go then. I am testing for the first time using Google screencasting software, Google Plus's sort of live broadcasting. So this will either work really well or it won't. One or the other, and we'll know. But today, and if this does work, it's kind of a neat thing in that I may start using it more often, in that I can kind of document each and every lesson, not just the note, but I could actually document sort of the joy of watching me give it. And isn't that exciting? Anyway, we're starting our 5th unit today, which is grade 11 trigonometry. And there's going to be some different components to that for between the two classes, but for today's lesson, we're all doing the same review. So this is sort of a review of what was in the grade 10 academic math class for trigonometry. And so we're talking first and foremost about right angle trigonometry. And of course, this is the measurement of triangles that have a right angle. And so I've drawn a nice little right angle triangle here. So we're going to recall that for any right angle triangle, we can define a few things. So I'm going to draw a nice right angle triangle here, and I'm going to draw it pretty big for the moment, because we're going to take a bit of time and actually talk about each of these things. So what defines a right angle triangle, of course, is that it has a 90-degree angle, a right angle. And I've drawn that here. And we're going to talk about what we measure when we look at a right angle triangle like this. And the first thing I want you to remember is that for any right angle triangle, we always have a longest side. And the longest side is always found across from the right angle, and it's referred to as the hypotenuse. And so there it is. And often we'll just call it h, but it's across from the 90. Now I'd also like to remind us that the other two sides we label relative to an angle that we're talking about. And we could be talking about either of these angles. It doesn't matter. But we're going to talk about this top one here. And we usually call that angle theta. All right, so over here we might mention that that is the Greek letter theta. So for any right angle triangle with an angle theta, known or unknown, we have the hypotenuse, which is always across from the 90. And then we have two other sides. And I'm going to give you 30 seconds to label them. We can pause the video. All right, we're back. Hopefully you remembered that we call the side across from our angle theta the opposite. It's not a complicated name. It's called the opposite because it is opposite from the angle theta or across from the angle theta. And then we label the remaining side adjacent. And hopefully you remember that adjacent just means next to or touching. So the adjacent side is next to the angle or touching the angle, and the opposite side is across from it. Now, why do we need to name the sides? Well, it's because of what trigonometry lets us do. Trigonometry basically is the relationship between the sides of the triangle and the size of the angle. So we're used to measuring angles in degrees, but what trigonometry tells us is that we can also define the size of an angle in terms of how big the sides of the triangle are. And that makes sense, of course. If we made this opposite side really long, theta would have to get bigger to keep this as a triangle, right? If the opposite side extended all the way out to here, then theta would have to get bigger to account for that. Likewise, if we made the opposite side really short, then theta would end up becoming smaller to keep it a triangle. So this angle theta really depends on how big the opposite is. Of course, it also depends on how big the other sides are as well. So we can define theta, we can define any angle in a right angle triangle in terms of these three sides. And hopefully you remember the three ways in which we do that. The first is we take a measurement of the angle theta, called its sine. All right? And we use a three-letter abbreviation for that, SIN. But it's not the sin of theta, of course, it's the sine of theta. And we said sine of theta is equal to the length of its opposite side over the length of its hypotenuse side. And I'm sure you all remember that. So the sine of theta is opposite over hypotenuse. The next one, of course, is called cosine. And I'm sure you remember that the cosine of the angle theta, which we often will just say cos, the cos of theta, is equal to not the opposite over the adjacent, but this time, not the opposite over the hypotenuse rather, but this time the length of the adjacent side over the length of the hypotenuse. And lastly, the last measurement of an angle, sine, cosine, and lastly, tangent. All right, and we say that the tan of theta is equal to its opposite over its adjacent. And these are just definitions. We said we can define how big this angle is if we know how long this side is and how long that side is. And we call that the sine. We can also define this if we know how long this side is and how long that side is. And we call that the cos of the angle. And the last thing is we know how big this angle is if we know how long this one is and how long this one is. And we call that the tangent. And to help us remember these, because it can be kind of tough to remember, we had that great nonsense word SOHCAHTOA. SOHCAHTOA. Sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, and tangent is opposite over adjacent. SOHCAHTOA. So that's our review. Now, what can we do with these two things? Well, as you may or may not recall, we can basically do two things. We can basically do two things if we know the sine, the cosine, or the tangent of an angle of a triangle. And the first thing we can do is find the length of an unknown side. And let's look at an example that asks us to do exactly that. I'm going to put the example up here, and I'm going to ask the teacher in the room to pause the video while you guys solve it, and then to start the video again, and we'll go through and make sure that you've all solved it correctly. But this should be review, so we'll try having you solve it first. But let's imagine that we have a triangle with an angle of 24 degrees. It's a right angle triangle with an angle of 24 degrees. The hypotenuse is 4.2 centimeters long. And across from that 24 degrees, we have an unknown side, x. And I, of course, want you to find x for this triangle. All right, so go ahead and take a minute and do that. Pause the video, and then we'll come back and see how we do. Okay, so hopefully you guys have already solved this, and hopefully you're going to find what I'm about to say very boring. But the first thing we have to do, just like we did up here, is label a triangle. So we have a right angle triangle, and we're going to label the sides. So the easiest one to label is always the hypotenuse. And we do that because the hypotenuse is right across from the 90-degree angle. And so there it is. Now, we remember that the other two sides get labeled according to our theta. And this is theta here. Our theta in this case is 24 degrees. We know the angle. So when we go across from that, we of course get our opposite. And the side that touches theta is called the adjacent. Once we've done that, we need to determine which ratio we want to use. Whether we want to use the sine, the cosine, or the tangent of our 24-degree angle here. We determine that by looking at the side we know, which in this case is the hypotenuse, and the side we want to know, which in this case is the opposite. So we know the hypotenuse, so we're going to make sure we use that. And if we look here, well, sine has hypotenuse, so it's possible. And cosine has a hypotenuse, so it's also possible. So we're going to be either sine or cosine. Leave that up there, I guess. And then we want to know the opposite. And tangent and sine both have an opposite. And if we look, once we've looked at that, the ratio that has both what we need and what we already know is sine. So in this case, we're going to use sine. I'm going to make a little note of that. We use sine theta because it has, well, we don't need to make a note of that. Actually, I take it back. We're going to use sine theta because it has what we need to know. But I'm not gonna get too pedantic here and clutter this. So we say the sine of theta is equal to the opposite over the hypotenuse, which we get from SOHCAHTOA. Sine is opposite over hypotenuse. It's our definition. It means that this angle depends on how big this side is and how big that side is. And as soon as we've written it down, we can substitute numbers in. So we write it again, sine, but not theta. We know theta. Theta is 24 degrees. So we say sine of 24 degrees is equal to, make our fraction, then opposite. I don't know the opposite. It's my unknown x. So we're going to put the x up there. And it's over hypotenuse, which we do know. That's 4.2 centimeters. And I'm not going to worry about units after this, but I'll put it here just because I'm a science teacher and I love units. We want x all by itself, so we have to move anything that isn't an x. We have to move the 4.2 centimeters to the other side. Now, of course, over here, 4.2 centimeters is involved in division. So when we move it to the other side, it's going to do the opposite operation. And the opposite operation of division is multiplication. So my next line should be the sine of 24 degrees times 4.2 is equal to x. Now, the nice thing is, maybe you're not familiar with seeing that dot for times, so maybe I'll just put that in a bracket as well. Point is, we're multiplying. The good news is we can just do this on our calculator. The one thing you want to be sure of is at the top of your calculator, it should say somewhere degrees. Degrees are good. It might also say radians, or it might say gradians. Degrees is good. We want it to say that. If, on the other hand, it says radians or gradians, that's bad. We don't want it to say those. And to change it, there should be a button on your calculator that says DRG. You should remember that. It flips between degrees, which is the unit you're comfortable with for angles, radians, which we haven't used yet. You'll use that in grade 12 if you carry on, and gradians, which you also use in grade 12 a little bit if you carry on. So just make sure that the top of your calculator says degrees. And if it does, we could just punch this right into our calculator. And it's as easy as sine 24 times 4.2 and equals, and it will give you the answer. And so when I've done that question here, I finally say that 1.71 is equal to x. And I'll answer the question. I'll say, therefore, the unknown side x is 1.71 centimeters long. So again, we put our ratio in, we put the numbers we needed in, we rearranged it, we plugged into our calculator, and we solved. And that's how we find the length of a side using right-angle trigonometry, which of course should be review. Now the other thing we can do with right-angle trigonometry is not find a side, but we can also use it to find an unknown angle. So we can use it to find an unknown side. We can also use it to find an unknown angle. Crazy things going on there. So if we need to do that, let's draw another right angle triangle. Let's say there it is. That's a right angle. Let's say that's, oh, fool me once. Let's say that's 4.1 centimeters. Let's say that this is 3.6 centimeters. And let's say that this is the angle theta that I want to solve for. All right, in fact, I'm just going to put an x there. That's what I'd like to know. I'd like to know the angle. So we're going to say, find the angle x. And we're just going to make a note in degrees. I want to know the actual degree measurement of x, so that if I wanted to draw this using a protractor, I could. How do we approach it? Well, you're going to decide that. We're going to pause this video again, and you're going to try to solve it. Then we'll unpause it, and we'll take it up again. So pause right now. All right, and we're back. So we're going to solve this. Just like last time, we need to label this triangle. Oh, no. Okay, I'm going to edit this video, so don't you worry. Don't you worry, this video is going to be all edited, because I said this was 3.6, and it, of course, is supposed to be 7.6. Oh, what a loser I am. Okay, so we want to find the angle x of our right angle triangle here, which I just hastily redrew because I'd written it wrong the first time, which is 4.1 centimeters, 7.6 centimeters. With the angle x there, we want to find the angle x. So we're going to pause the video and let you solve it yourself. And we're back. So the first thing we have to do with our triangle here is label all of the sides. I always start with the hypotenuse. It's across from the 90. So there's the 90. We go across. And we say, there is the hypotenuse. Now we remember the opposite and the adjacent depend on our angle theta. There's our angle theta. We go across from our angle theta, opposite our angle theta, and we get the opposite side. We go next to our angle theta, adjacent to it, and we get the adjacent side. And now we've labeled a triangle. I might even put a theta there so I know which side is which. Now we again have to remember that we want the adjacent and the hypotenuse, because those are the two sides I know. So in SOHCAHTOA, cosine has an adjacent and tan has an adjacent. Sine has a hypotenuse, cosine has a hypotenuse, and in the end, cosine is the one that has both ratios that we need. So in the end, when all's said and done, that's the ratio we need. Wow, I really struggled to erase that. I don't really know why I bothered. But there we go. So we're going to use cosine because cosine involves the adjacent and the hypotenuse, and I have numbers for both of those. So we'll say the cosine of theta is equal to the adjacent over the hypotenuse. Just like that. And once we've done that, we can rewrite this and sub some numbers in. So we can say the cosine of theta is equal to 4.1 centimeters, because that's the length of the adjacent, over 7.6 centimeters, because that's the length of the hypotenuse. And it's here that we need to remember our grade 10 trigonometry, which is sine inverse, which we denote as sine with a -1 up here, but we call it sine inverse, cos inverse, and tan inverse find the angle theta when we know what sine theta is, what cos theta is, or what tan theta is. So we can use these inverse functions to go from the cosine of an angle to the angle itself. So if the cosine of some angle theta is 4.1 over 7.6, we can use the cos inverse to get the angle itself. And so if we really wanted to show it, we could really say this. We could say it's like the cos inverse on the left and the cos inverse on the right. We do the same to both sides. That's the cos inverse of cos theta equals the cos inverse of 4.1 over 7.6. Now, the cos inverse of cos, those are opposite operations, right? The whole point is that cos inverse cancels cos, and it will get us just to the angle. And this leaves us just with theta equals the cos inverse of 4.1 over 7.6. You don't ever need to show this step. I'm just showing that we are doing algebra. We're following the rules. It's that these are opposite operations. Taking the cosine of theta and then taking the cos inverse of that just leaves you with the original. It just leaves you with theta. But just remember that if you have a cos theta, you can take the cos inverse of the other side, and it'll give you the angle theta. And this we can just punch into our calculator. Now for you probably will find that using the second function button, and it'll be second function cos. And then I would open a bracket, though you don't necessarily need to, but I love brackets. 4.1 divided by, or you can use the fraction button here if you have one on your nice fancy calculator. 7.6. Close your bracket and press equals, and that'll do it for you. In my case, I'm going to use one note here, and it just calls it the arc cos or the acos, but you don't need to worry about that. And it will do the math for me, and it will tell me that the angle theta is equal to 57.4 degrees. And it's worth keeping in mind that this isn't something you can figure out mathematically. Really, it does have to look it up on a chart, so you have to use your calculator to do it. It's the only way. You need a good calculator to do so. So you use the second function cos, and it gives you the angle. As long as, just like you did here, you make sure you're working in degrees and not radians and not gradians. It will give you a nice angle measured in degrees that makes sense to us. So yes, it's true that the cosine of this angle is 4.1 over 7.6. We could even turn that into a decimal. But a cosine of 0.5395 doesn't mean much to us. We can't really picture that. But I think most of us can picture an angle of 57.4 degrees. And so there it is. And then, of course, we always like to actually answer a question. So I would make a therefore statement. I would say, therefore, the angle theta, or the angle x, right, is 57.4 degrees. Done. And that's all you need to know. So that is today's review lesson. I'm going to hand you out some worksheets that are just lots and lots and lots of practice in doing both of those. Hopefully it seems very much like review, but these are skills you're going to need to know for the lessons we're going to start on Tuesday. So I hope this helped. I'm sorry that I'm out again. I feel vaguely degenerate about it all, but such is life, and I will see you all on Tuesday. Have a wonderful long weekend.